All right. So yeah, welcome everyone to the last day already of the Agda meeting. And we have one more talk today by Musa Al-hassy on do-it-yourself module systems, unbundling on the fly, and mechanically obtaining term types from theories. So please go ahead.
Thank you for introducing me. So I'm really excited to be doing this talk. I hope you are as well. So the overview of this talk is just with a bit of reflection in Agda. We can obtain a uniform and practical syntax for both records and the algebraic data types. On the fly unbundling. So James was talking earlier about how to get type classes from records. So hopefully we'll see a little bit of that. And finally on mechanically obtaining data structures from theories. So we'll look into that a little bit more. So how to get the natural numbers from dynamic systems or trees from collection types. Okay, next. So just quickly, I'll go over the unbundling problem. Hopefully not take too long. So we have a bunch of things that we want to be able to combine, and we have a do nothing value, right? So in Agda, you just the same old thing that everyone's probably seen here. Nothing too interesting. The main interesting thing is that we're making the carrier a parameter. So this is a type classes approach. So that otherwise nothing new here. And we'll do some instance search, right? So programs and composition, numbers and addition. Now the common one that comes up in the Haskell community is numbers and addition or numbers and multiplication, right? So what is the monoid on naturals? When you have type classes, you essentially, it's a dictionary lookup according to the carrier type, right? So if you consider the carrier type to be the naturals, then you can define a type class on them. And then using type class, using instance search, the composition operation is known to be addition because we look up the associated instance for monoids by according to the carrier, which is the natural numbers, right? Yeah. Right. So likewise for other fields of the type class data type. Okay. But if we consider a multiplicative approach, then it's not clear anymore. When we say M and then identity, there's two conflicting candidates for the type class on the natural numbers. So there's no unique solution, and an instance search in Agda will fail for this. So alternate approaches are to consider, for example, named type classes, or as we do in Agda by having records and then passing them in as names. The Haskell community instead says, let's have two copies, one of them called sum and the other one called product. This duplication is not that ideal, I think. And so we'll look at a different approach today. All right. So we'll try to do unbundling in Agda by starting with a fully bundled monoid type, so no parameters at all. And then we'll expose fields as parameters on the fly. Okay. So we'll do this by reflection, right? Unfortunately, the current reflection mechanism for Agda doesn't let us touch records directly. I cannot inspect a record and then produce a new record from that one easily with the current reflection mechanism. But theoretically, every record is a sigma type, right? Theoretically. So a normal syntactic sugar like this, in Agda record R, and then you have some parameters epsilon 1 to epsilon W, and you have some fields epsilon W plus 1 to K. We can see it in a more raw form as pi types followed by sigma types. This is very difficult to work with, I think. The syntactic sugar is very nice because it gives us projections, whereas this form doesn't give us as much. It doesn't look that nice, and you kind of need to end with the unit context, the empty context at the end, right? So going forward, we'll find a more practical and pragmatic notation, much closer to the way that Agda syntax sugar looks like. But for a moment, just bear with me with this ugly looking pi's and sigmas. So this is really just a partitioned context, right? We have the parameters up here. Then we have a bunch of sigmas for the body of the record. And then we end uniformly with the empty context, okay? I'll refer to this W number as the waist going forward. And so R is a sigma W, a pi W sigma type, okay? So in particular, the monoid on type class we saw earlier is a pi 1 sigma type because it had one parameter, okay? But unfortunately, if we encode using these pi sigma types, again, it's not clear if we want to go into the body somewhere in the sigma types and instantiate one of those fields. So we have to lift it up as a parameter. Okay, so the same problem rears its head. So we need a way to lift parameters to fields, and this is an operator we're calling reification, or pi to lambda. All right. So instead of working with records that are specifically parameters to set, we said, let's work with fully bundled records. So there's no more parameters, it's just set. But then we said, wait a minute, if it's just set, I need to lift some parts up. And how many I need to lift should be on the fly. And so we'll call that the waist. So now we're moving to contexts, okay? So contexts are exposure index types, right? The empty context is the unit type, right? And to make it all look nice, we have do notation, right? The do notation right here says, you know what, when the waist is 0, we're at the body level, so make sigmas. When the waist is not 0, then we have a parameter, and so make a pi, right? And the DIY in the title is from the fact that you don't need to use sigma or pi right here. You can use W types for well-founded trees, or if you want, you can use let clauses to make definitional extensions. So this is this small part of the core library is where the DIY comes in. Right? So let's look at an example. Here is the monoids from before. Notice that using do notation, it looks really, really similar to the syntactic sugar we have with Agda records. Right? Instead of the word field, we just say do. Instead of a colon, we have these arrows everywhere. And we unfortunately need this end, right? Which is not a big deal. Before we said record, monoid, where. So now we just have an end clause, right? And happily, this all type checks, and that's fantastic. And just as before, when we had a record with the named fields everywhere, with thanks to Agda's unifix mixfix lexemes, we can make some nice constructor patterns that are that work everywhere. And so we can define an instance on the natural numbers. The cool thing here is that the type class on monoids we started with is now a particular instance of this waist operation, in particular waist 1. We're exposing one element of the monoid, right? Sorry. So the monoid had a carrier, and we're going to lift this carrier up to the type level. So that's what the waist 1 does, okay? And then the remaining elements become the body. Right? So we lifted the carrier up. Oh, sorry about that. Sorry about that. Okay, so we lifted the waist, we lifted the carrier up to and instantiated it to the natural numbers, and the remaining artifacts become the body. Okay, and it all looks reasonably nice. Okay, so now that we saw an example of what this waist is, let's talk about it just a little bit more. So we said a moment ago that records are the same as contexts, right? Sequences of name type pairs. And a context, we said, is an exposure index type. right? You can decide how much of the structure you want to be at the type level and how much you want to be at the body level, okay? So to actually use these contexts, we use this pi to lambda operation or reification, right? So I'm just going to write pi to the power of lambda, pi to the power of w to indicate w many pi's happening, right? So if C is a context and we expose w many parameters, that means there's going to be w many pi's happening, right? For each possible parameter. And then at the very end, you get a set. So this is just like when you declare a parameterized record. Parameterized records have a number of pi's, and then they're of type set, then they have a body, okay? But to actually apply these, so a context is again, just an exposure indexed family of sets. Then you can apply an exposure to get something of this form. And then to actually apply it, you need to transform the pi's into lambdas. So instead of having w many pi's, you want to have w many lambdas corresponding to each argument, to each parameter, okay? And we'll also use this infix form, C colon waste, just to look a bit nicer. Okay. So let's just look at a few examples just to see what this looks like before we look at the implementation. So recall a monoid was a carrier that comes from set, and then an operation, and then identity, and a bunch of invariants, right? So with no parameters, we have a sigma zero, a pi zero sigma type, right? So we have no parameters. This is just a set one. There is a set, an operation, an identity, and some more invariants. With one parameter, this is what James was talking about earlier, we get a type class formulation, right? So a pi1 sigma type is a type class. Notice, this is the big difference right here. Before at 0, we took 0 arguments. Now at 1, we take 1 argument. And then to actually apply the 1 argument, the pi becomes a lambda at the body level. So monoid waste 1 is a type former that takes one type and produces another type. Okay. And then when we have 2 parameters, we essentially solve that earlier problem of do I have additive monoids or multiplicative monoids? Instead, now we can speak of monoids on a particular set and a particular operation. So I want monoids on the naturals with plus, and I want monoids on the naturals with times, right? And because this is on the fly, the library designer simply works with monoid, and the user can make code against monoid colon waste. Okay. The colon waste syntax is inspired from the Lisp language used for Emacs. Originally, the library was written as a prototype in Emacs Lisp with Emacs metaprogramming, Emacs Lisp metaprogramming, and colon is what they used for keywords. And we've simply inherited that, and it looks sufficiently nice. Okay. So just to reiterate the main relationships, the moment you have a context, which is an exposure index type, you can apply it to get a pi w type, but then this pi w type, to actually reify it with some parameters, you need to use the underlying pi to lambda operation or waste to make it into a lambda. Okay, so let's talk about the implementation really quickly. And thanks to Ulf, it's really, really short. Okay. So at the syntactic level, all we're doing is taking pi's and replacing them to lambdas. So really, really easy, right? Not a big, not terribly difficult. And hopefully, by showing these simple implementations, it's the hope that other dependently typed languages will be able to provide these features as in-library mechanisms. Unfortunately, the type of reflected terms, the abstract syntax trees, is actually not typed. And so Ulf's idea was to keep track of the types as we go along. So if we have a pi type, we keep track of its type, and everything else, we don't know its type, and so we can ignore it. And then we just stick the two together, right? As a macro, we are given some type. We normalize that type. Then we, because it's a term type, we've lost all the typing information. So we regain the typing information, and then we transform all pi's to lambdas. Okay. So really, really easy, not too difficult, hopefully. And this is one of the neat lessons we've learned by doing this project. We had a lot of times where we needed type class variant, or we needed to expose more pieces, and we thought we should be able to do this. It shouldn't be that hard, and luckily we were able to. So that was nice. Then we thought, wait a minute. Sometimes you make you have a semantic model of a theory, like monoids, and you realize it would be really, really nice if I have a syntax. If I have access to a syntax, not a reflected metaprogramming syntax, but an honest-to-goodness algebraic data type that I can pattern match against and then perform optimizations. And it's specific to a particular problem I'm working on. It's really unfortunate that I have to mimic my syntax according to my semantics. Right? My algebraic data type has to be mimicked from my record. We thought maybe we could derive one from the other. And we were successful in the Emacs list prototype. And so we said, let's do the same thing at the Agda level. So here's the motivating calculation, very informal. So I'll use these squiggly arrows to denote steps in this informal calculation. So recall monoid was a carrier set, an operation, and identity, and then some more invariants. Then we want to be able to, an algebraic data type has only one carrier, which is the algebraic data type being defined. And everything else is in the body of the algebraic data type construction. So we can apply waste 1 to turn this into a lambda sigma type. But then you'll realize we only keep the elements of the body that target the carrier. For example, when you have lists, the empty targets list, and const takes 2 arguments and targets list. There's nothing that does not target list. So likewise, if we're making a term type, and our term type is going to be called C, then all the operations have to target C, and we had a bunch of invariants. None of those invariants targeted C. They were all propositional equalities, and so they're dropped, and we have our familiar terminal type. Okay. But wait a minute. When you talk about, for example, lists again, they target C, but they're really determined by their arguments. The empty list doesn't take any arguments, and it targets the type of list C. So we take no arguments. The const construction takes 2 arguments, and then it targets C. So we turn that into a product. So we walk along all the body constructions, and we get only their sources. We get the sources from each one, and then we turn that into a union, because an algebraic data type is a sum of products, right? A simple one is a sum of products. And then finally, an algebraic data type is a fixed point of a sum of products, right? A W type, or a well-founded tree, okay? So the idea is to start off at a context, and then to automate these steps, and hopefully end up with something like this, okay? And just as before, we don't really want to work with ugly representations, so we'll find pragmatic, practical ones to actually make using this approach realistic. So as I mentioned earlier, we look at the type, we get all of its sources, all right? So we drop the target from each one and turn repeated arrows or pi's into sigmas or products. And then we transform all sigmas into disjoint unions, and then we form the fixed point of that, okay? And it's also not a terribly difficult or interesting macro, so we won't go too much into it. But let's look at some examples. All right. So recall our, handy dandy monoid, untyped composition, as it were. One thing to notice is the construction of term type macro, as just as a design decision, is any element of the context which starts with implicits is considered an invariant and will be dropped. So this is just a design decision. It's not very deep and it can be easily changed. Just for brevity, we're saying if it starts with an implicit, it's an invariant. So in particular, these guys are considered invariants and they will be dropped, and everything else is a function simple and will be kept, okay? So we use the macro term type, right? We want a monoid at level 0, right? So just to show that we support levels. And as always, we're just going to say it's a waist 1, right? So monoid at waist 1 is the type class. This is a type former. Term type takes a type former and produces an algebraic data type, okay? And we can show with a simple reflexivity proof that this term type is in fact going to have the operation, the binary operation is going to be branching. Then the identity is going to give us a leaf, and then all the other invariants are going to be thrown away, including the end of the context. It's also thrown away, right? So it's nice that we can even show this equivalence. So that's pretty neat. So again, this looks really, really ugly if you work in terms of all these injections into fixed points. It looks very, very ugly. Luckily, we have patterns in Agda. And if you can't use patterns, we can also make a very nice macro, an injection macro that makes programming with these things very easily as well. So hopefully many languages will be able to provide an injection to make all of this one injection call. But since we do have macros and we are talking about Agda, the empty macro, right, is a value of this term type. This branch M, it takes 2 and returns 2, and then everything else is an absurd value. So with these suggestive names, we have an idea of what this type looks like. It's the skeleton of trees, right? So recall that a tree skeleton is either the empty tree or the branch of 2 trees, right? So we're not considering labeled trees right here. And then if we do nothing, essentially, empty goes to empty. So the patterns make this very suggestive and really easy to program and prove. The empty constructor for boldface M just goes to the empty constructor for trees, and likewise for branching, right? And then we have some empty clauses. I just wanted to show them for completeness. But if we didn't use patterns, this would look terribly difficult to believe. Suggestive names definitely help. And likewise, we can do nothing the other way. Every tree gives us. And just by definition chasing or normalization, these two are inverse to each other. So that's pretty neat. And this is not a new idea that monoids give us trees or lists. But what is kind of new is that we were able to get this mechanically. Right? We just said, here's the theory of monoids. What's the term type? And then we're like, let's give these suggestive, useful names. And then we're like, oh, this is just tree skeletons. Oh, that's unexpected. Why is it tree skeletons? So let's look at another one, just for fun. So here's a dynamic system. A dynamic system, there's a bunch of states. There's a button that you press next to move between the states, and you have a start state, right? So like a finite automata or a Pepsi machine, right? Very simple, nothing too difficult right here. Then we ask for its term type. We're just saying, hey, please lift the carrier out. So make the start state a lambda now. So this is a type former. This is the type class of dynamic systems. And term type takes type classes and produces algebraic data types. Okay. Then we, as we did before, we'll add pattern synonyms to make it more readable. So we call one of them start and the other one next, right? And the names are again very suggestive from the context, right? So we don't need to know what term type is. We just say, oh, we had a start button and we had a next button, and we can just name our patterns respectively. We don't need to be clever about it. And then we realize, wait a minute, if we look at the types right here, start is a constant and next just moves us in this space, and we have a name for this thing. This is the natural numbers, right? And again, we're essentially doing nothing. The patterns do all the work for us. Start goes to 0, and next goes to suck, and suck goes to next. So this is pretty neat, right? It's not a meta-theoretical observation, but rather it's an in-language observation that you have this exposure indexed family, you produce a type former from it, you request the term type, and then you get natural numbers. That's pretty neat, I think. So let's look at pointed sets. Right? Just as another example, you have a set and you have a point. Not too interesting. You as usual, take the pointed set and turn it into a type former, and then ask for its algebraic data type correspondingly. And then you realize, wait a minute. So I didn't make the pattern here, but this is just the terminal type. So that's pretty neat. And the word terminal was chosen specifically to allude to possible categorical connections here. Right? So that's pretty neat. Graphs this is a bit surprising, but a simple graph for any two nodes will give you an edge. Or you can think of, instead of node, you can think of these things as values, and instead of edge, we have truth values among elements. Given two elements, are they related somehow? And we can, again, this time we're lifting with 2 though, right? The first one, node, becomes the, we're making a graph on things. So it's not a nullary algebraic data type, it's a parameterized algebraic data type. So this is an algebraic data type that is a type former. And so we lift 2, right? We lift the first 2 carriers out. And what we're doing is we're essentially saying, oh, hey, edge is the carrier of the algebraic data type, right? So as we did that process before where we only kept things that target edge. So we walk along the remaining elements and we say, oh, agency has an edge, so we keep it, right? So that's what term type does for us. And we realize this is just vertices. So that's pretty neat. We can give it a nice pattern, and we realize, hey, any syntactic graph corresponds to a pair. So that's kind of neat. We have a nice representation of these simple graphs. And this one seems a bit strange until you look at it a bit more. Indexed unary algebras or actions give us infinite lists or streams. So I've chosen some suggestive names just to make it accessible, but I think everyone here knows much more than I do. So you just have an index type and then a family indexed by the index type. And then here's the operations. All right. You give me any index and I can apply it to get another one. Right. If we ask for the term types, again, using waste 2, and we give a suggestive name, the name is very suggestive. So it looks like we're doing nothing, right? And just make the, go full circle. Here's the usual stream type in Agda. And you can define it by co-pattern matching because it's a co-inductive data type. And the head is just the head and the tail is just the tail. So that's really neat, I think. This one I think is kind of new. I don't think this one's been mentioned before in the folklore. We started with monoids, so let's wrap up with list. How do we get lists? And we thought, wait a minute, we want to have a collection type. I want to have some sort of elements some sort of container, and I want to be able to insert things into my container. If we ask for its term type, again, using waste2, and now we have a parameterized algebraic data type, taking some type elements and producing some type of collections on them, syntactic collections. And then here's some suggestive names, right? We have consts and we have the empty list. And I won't bother with the to and from. And so, yeah, we have all these useful data structures that we use in programming coming from theories. So that's, so I just showed a little bit. There's a lot more small theories, and they can show a lot more interesting things. And I thought it was a lot of fun, and I hope you had a lot of fun too, listening to me. And yeah, thank you. Do you want to talk, or do you want to have questions? Yeah. Do you want me to show you some code?
Well, thank you for the talk.
Okay.
Maybe we should start with some questions, and then can look at the code after that. Or
yeah,
on how much
I'm
time
happy to do both.
Yeah. So. So there was one question by Guillaume on the Zulip. If you want to ask it yourself, or should I ask it?
Please go ahead and ask it, or I can open up Zulip.
No, I'm asking Guillaume.
Oh.
If you want, okay. Maybe I'll ask it. So he's saying, so the dependency graph between the records fields is in general directed acyclic graph, but you have a linear representation of it. So does that mean that your approach is limited to converting a prefix of the context into parameters? Or would you, for example, for the monoid example, also be able to get a monoid where you fix the identity field, but not the operation?
Yes. So this is unfortunate. In the Emacs Lisp implementation, you can fix different pieces because it's a directed acyclic graph. You say, I want to keep only these parts to get a substructure. Or you say, I only want to fix these parts. And so only those parts and the pieces they depend on are pulled into the type level. So this is possible in the Emacs Lisp representation, implementation, which produces full-fledged Agda. But in the in-language one, it's unfortunately not as clear-cut, specifically because of the, where is it? Specifically because of the bind operation. Sorry, where did I have bind? The bind operation, which gives us that nice do notation. So if we sacrifice the nice do notation, we might be able to do it, but that's not desirable. So that's the short answer. Here's the bind. Sorry, here you go. I hope it's not too small.
That's fine. Yeah.
So,
but you could imagine having a operation on the context that on the reflected syntax of the context that tries to swap two of the fields, basically.
Yes.
But then you would have to do like a free variable check to see that they can actually be swapped.
Exactly. So in the Emacs Lisp implementation, it's all strings all the way down. It's hooked into the Control-C, Control-L of the Agda Emacs interface. So it all happens in the back end. Because it's all strings, we can easily just look at the strings and try to find syntactic textual occurrences. It's a bit difficult with the term type for Agda's reflection mechanism. As you mentioned, trying to identify free variables is trickier than it looks because it's all De Bruijn indices. So it's not as clear cut, and I haven't been able to do it yet.
Okay. I think do we have some library support for that, for strengthening and such? Ulf, do you?
I'm sorry?
Yes.
No,
yes,
I'm asking Ulf.
Yeah.
Because he has some library for that.
I talked briefly about this in my talk, right? And this is in the library right now. So I think that part has strengthening and weakening and checking if a variable is free.
Okay.
So you should be able to make use of that maybe of Ulf's library, so that you don't need to implement this De Bruijn magic yourself.
All right. Yes, I really would not like to implement too much De Bruijn magic myself. Thank you for letting me know.
Okay.
So,
so there was another question by Orestes. So he asked if it would make sense to for the waste operation to now you just have a number for the number of arguments, but to instead give a list of the names of each of the arguments, so that you can actually give the names.
Yeah, that would definitely make more sense when you're saying I want a number of them. And using the Emacs list prototype, we actually were able to say, hey, I proved this theorem in monoids. What is the smallest structure that will allow me to prove this theorem, right? And the system just essentially it looks at all the textual occurrences and then finds the smallest theorem that will allow it. So if you proved the idempotency of the identity in monoid, what's the smallest theory that will allow you to prove that? And the system produced something called left unital semigroups. So I agree. When you have access to names like that, you can do much more interesting things.
Right. Yeah, another question I had is, so now, well, you were kind of forced to use these pi sigma types, or this representation of record types, rather than actual Agda records, because you cannot generate them yet. So is that the only reason that you did it this way? Or now that you did it, maybe you can see other advantages of this approach? Or would you just port it over to to use actual records if that were to be implemented?
The main insight was that records are just context. And then from proof theory, when you see that you have an entailment, you have a bunch of premises and then they entail a result. And it was this idea that the premises of an entailment are like the parameters, and the result is like the body. And we realized, wait a minute, if you want to have multiple results in the body, you can have a conjunction using the entailment theorem. And so the idea, okay, if you have a conjunction using Curry-Howard, you have a bunch of sigmas on the right side of an entailment. And then if you have a bunch of assumptions, this is a pi. And so that was the relationship between the two. And then we thought, what about when you move things around? And so that was essentially it. And the difficult part was really getting do notation to work. We could have worked with pi sigmas all day long, but I don't think it would have been as attractive or desirable. This is, and using the do notation, it looks much closer to record types. Unfortunately, it doesn't support implementations yet. But I know that Jesper, you wrote some cool reflection code on allowing default implementations using tactics. So maybe looking in that direction might extend the abilities of these contexts.
Okay.
And if you're using actual honest to goodness record types, you couldn't do the on the fly thing, right?
Yeah, I couldn't.
You'd have to lift. You'd have to say, "Oh, here's the record type for lifting the two-way thing." You'd have to declare that once, and then.
Yeah. Right. So we'd have to generate a separate record type for each different number of arguments. Yeah. Or number of parameters. Yeah.
Yeah. So in the Lisp prototype, whenever you say, "Oh, I really want to use this," if it's not generated, we just generate it. There's an auxiliary .agda file with a bunch of generated stuff. And you're like, oh, it would be nice to have this. It just gets generated in the backend when you press Control-C, Control-L. And we did some stuff like that with reflection where If things don't exist, we try generating them. Using the fresh name construct, unfortunately, even if we generate them, you can't use them. And so that was problematic. And we haven't been able to do that just yet.
Right, that's another current limitation, I guess, of the reflection machinery, that, well, you can generate names, but you cannot you cannot generate names that you can refer to later on in the file in actual code.
It's been fine to make to give us a nice syntax for unit tests. And now we say check mark, and then we can generate a silly name that's inaccessible, and it's a nice little unit test. So I found some use for inaccessible fresh names.
Okay. I see there was another question by Orestes on the Zulip. So he's asking, like, what are the advantages of doing this using the Agda reflection rather than compared to the Lisp or the eLisp script that you had? And in particular, are you planning to prove anything about this transformation in Agda itself?
So unfortunately, haven't actually been able to prove much since it's mostly textual. But we have been able to get here. Let me. I think I have some actual examples to show. We haven't been able to prove much since it's mostly textual, but we've been able to phrase things in such a way that we can get a lot of these reflexivity proofs. And we found a lot of opportunities where having these features would be nice. For instance, when you call term type, you essentially find out if the term type construction works or not at runtime. So we've essentially delegated all of our proof obligations to the type checker. So that's what we've done there. But just for example, sorry, here is a here's an example for instance.
Could you make that a little bigger?
Oh, sorry about that.
Maybe put it full screen or something.
Yeah. Is that a bit bigger?
And maybe zoom in a bit more. Yeah, that's fine, I think, for me at least.
All right, I'll zoom out a little bit more then.
Yeah.
Here's some of the stuff we can do with the Emacs interface. For example, I have a magma type. If only I can find it. And my magma, I have a monoid type, and my monoid type is able to show that the identity element is unique. And I want only this proof. I want the monoid type, and I only want this element. And of course, it's dependency graph. And then when we ask for this, the system generates this nice thing. It says, you know what? Here's the smallest record that will allow you to continue to have this field. And so that's pretty nice. And we were able to essentially take some 1,500 lines of type-checked Agda and render them in about 200 one-line specifications. So the Lisp interface is just Control-C, Control-L, and it happens in the background, and you put things in these interesting comments, and you can extend the number of module creating combinators as you like. So I would say the prototype is much more useful for real work. You know, if you actually want to have a lot of theories, if you want to have a lot of type-checked Agda and you have an interesting hierarchy, I would recommend using the prototype because it will generate all these interesting relationships for you, and it type checks, and it's usable. And users of the library don't need to know about the prototype at all. Whereas the context is much more limited, but it is within Agda, within a dependently typed language, and everything type checks, and it's all abstract syntax trees instead of a string manipulation. So I would say they're somewhat complementary. For getting real work done, for actually reducing the amount of boilerplate one needs to write. Just installing the Emacs package would be much more beneficial. But for exploratory research, the context library, I think, would be the way to go.
Okay. Yeah.
And
Nice.
so if I can jump in here, like the current handwritten library has between 20 and 30 algebras defined, each of which is a non-trivial block of code. Here, essentially, they're all one line, and there's 200 of them over 200 lines, because they're all related to each other by various operations. And here, not all of the utilities are generated, but that's because they're all flattened. And so there's no nested records. This is a design choice. Musa's flashing stuff by too quickly.
But here's just as you were mentioning, Jacques, if you do want these design decisions, you can get them. When you say extended by, you get these other pieces as you like. There are these coercions if you ask for them. It was, as you said, it's a design decision not to have them all the time there.
So to be able to do this, like you take the magma here where you say extended by blah, blah, blah to record. Is it only being able to construct new records using reflection? Is that the only thing missing?
Yes.
For this?
Is that true?
Essentially, these extended by, they inspect records and produce new records. So they're just these are just raw functions that look at a context and then produce a new context.
Well, so
that's what the ability is really to inspect
Yeah,
Agda
so
records.
you can at the moment, I believe, you can inspect records, right?
Yeah.
record declarations, right?
Yeah, but you can't actually produce them. You can't produce
But
them.
what's missing is actually creating a new record from that.
Yeah.
And then giving it a name at the top level.
Yeah. Well, but the name you're giving it here, right? So
Sure,
the name
yes.
is actually this type or magma in this case, right? So
Oh.
so here you're actually declaring the name. So the name part, I don't think.
Yeah, the name of the record type, but not the names of the
name,
fields.
the projections, yeah, the fields.
You
I
also
mean,
want those to
the-
be in scope, right?
Yeah, that's the main reason why we don't let you do that right now, right? It's hard for data types and records to know how do we deal with the names of the constructors and the fields.
So one idea would be to have like a top level declaration to just declare a name that is then available for use in reflection. And then, I mean, since these are usually overloaded names, right? So you would declare then, yeah, I don't know exactly, but I mean, maybe we can do something like that.
Yeah, but even overloaded names, like each name is different internally, right? It's just
right. Yes.
The string, the concrete name is the same.
Mm-hmm.
So somebody asked the question, why do this in Agda? Well, so the chances of it going wrong are less than the Emacs Lisp one. There is quite a lot of string munging, which is, as we know, not the best form of metaprogramming ever. Second, we kind of would like to know how much of this needs metaprogramming and how much of this is straight programming, like a better barrier between the things that are just code and the things that really do need introspection. And can we make that as thin as possible?
Sorry, go ahead. So by writing it out as a library, it's you know, just how many occurrences of the word term are there essentially shows shows how much of this requires reflection, metaprogramming. So I guess that's one benefit of looking into it. Or rather, how many macros are there? There's essentially 6 macros here, right? So to make this happen, that's nice. I guess that's one benefit of doing it in Agda. It's you have a cleaner distinction between actual classical programming and metaprogramming.
And then my aim, of course, would be to reduce that further. And again, even though I do a whole lot of research in metaprogramming, one of my motivations is actually understanding it well enough to eliminate as much of it as possible, because it should just be programming. Metaprogramming seems to be a hack that we use to program stuff that our language doesn't let us do yet.
Great. I saw some quote on Twitter recently also that tactics are just theorems that we don't know yet how to prove in general. Or something like that.
Yeah, well, though I guess in some sense, some of your, so I was thinking of intro as a tactic, the simplest one you can think of, but actually that is one of Musa's, like moving something, like moving a pi out of the way to make it a lambda is exactly one of the combinators here.
Oh, that is pretty neat.
Okay. Are there any other questions? If not, well, we can still, if there's some questions later, we can continue the discussion on the Zulip.
Yeah.
So yeah, thanks again for the talk. It was great.
For having me. So
I'll end Twitch stream here.